Hello all, welcome to Scientifax. In this video, we will be discussing the three laws of planetary motion which is formulated by Johannes Kepler. Before we move on to the three laws of planetary motion, it will be useful to know more about Johannes Kepler and how he figured out these laws. Johannes Kepler was born on December 27, 1571 in Weil-Darmstadt, Württemberg, Germany, and died in November 15, 1630 in Regensburg. This is the picture of Johannes Kepler. Kepler's laws of planetary motion in astronomy and classical physics include laws describing the motions of the planets in the solar system. They were derived by the German astronomer Johannes Kepler, whose analysis of the observations were made in the 16th century. Danish astronomer Tycho Brahe enabled him to announce his first two laws in the year 1609 and the third law nearly a decade later in 1618. Kepler himself never numbered these laws or specially distinguished them from his other discoveries. Kepler's first law was the law of orbit. This law states that every planet is located in an elliptical orbit around the Sun, with the Sun situated at one focus of the ellipse. Understanding the first law. Kepler's first law of planetary motion states that the orbit of a planet is an ellipse, with the Sun located on one of the two foci. So there are two foci on the major axis, and the Sun is situated in one of them. Contrary to many people's beliefs and understanding, the orbit that the planets move on are not circular. So in the ancient times, it is also common conception that the orbits through which planets revolved around any object was circular, but that's not true. The Kepler's first law of planetary motion explains the real shape of the orbits, which is elliptical. A circle has fixed points that are equidistant from the center, unlike an ellipse which consists of points with a certain distance from 2 points, which are referred to as foci, as we said. The foci are situated on the major axis of the ellipse, such that the sum of the distance between any point on the ellipse and the two foci is constant. So the foci are situated in the major axis. This is the major axis of the ellipse, such that the sum of the distance between any point on the ellipse, so the sum of the distance on any point of the ellipse and the two foci is always constant. Kepler's second law, the law of equal areas. The radius vector drawn from the Sun to any planet sweeps out equal areas in equal intervals of time. This is called the law of areas. Understanding the second law. Kepler's second law of planetary motion describes the speed of a planet traveling in an elliptical orbit around the Sun. It states that a line between the Sun and the planet sweeps equal areas in equal intervals of time. Thus, the speed of the planet increases as it nears the Sun and decreases as it recedes from the Sun. In this picture, we can see that this imaginary line sweeps out equal areas in equal intervals of time. These are the imaginary lines, and they sweep out equal areas in equal distances of time. So therefore, that is why it's called the law of equal areas. So if a planet approaches perihelion, as we see, this is the perihelion. It is traveling faster than if it is an aphelion. This is the aphelion. In the perihelion, the line connecting the planet from the Sun is very short. So the perihelion is this and the line is very short. This is the aphelion and the line is very long. But since the planet moves faster, it covers a lot of distance. In the aphelion, the line segment is very long. But Mars also moves slowly. Not only Mars, it can be any planet. So anyway, they cover equal areas in equal intervals of time. This is the vocabulary. Perihelion. A point in the orbit of a planet which is closest to the Sun. As seen in the figure, this is the orbit which is this is the point which is closest to the Sun. Aphelion, which is the point which is farthest from the Sun. Major axis is the longer axis of an ellipse passing through its foci. As we saw, the major axis passes through two foci and the sun is situated in any one of them. Semi-major axis. The semi-major axis is the mean value of the maximum and minimum distances and of the ellipse from a focus. So it's half the size of the major axis, the semi-major axis. Kepler's third law, laws of period. The square of period of revolution of the planet around the sun is directly proportional to the cube of the semi-major axis of the elliptical orbit. This law is also referred to as the harmonic law. AR cube. That is the equation to remember. T is the time period, the square of the time period. And this is R is the semi-major axis, the cube of the semi-major axis. Understanding of the third law. T is the orbital period of the planet. The variable A is the semi-major axis of the planet's orbit. The major axis of a planet's orbit is the distance across the long axis of the elliptical orbit. The semi-major axis is half of that. This may seem very complicated, but it is not at all. So yeah, this is the major axis as we already have been discussing for the whole video. This is the perihelion, this is the aphelion planet. Semi-major axis is parallel to the major axis. It's half of that. T is the orbital period. A variable A is the semi-major axis. A major axis of a planet is the distance across the long axis. This is the long axis. Semi-major axis is half of that. This concludes that. This proves this equation. Thank you very much for seeing this video. Don't forget to like, share and subscribe to the channel and comment for a next video idea. Thank you once again.